Alrighty, we're back. Good morning, lads and ladies. This is College Algebra, MAC 1105, and today we are going to spend our second day talking about quadratic functions. So that's the move. As promised, today I am going to help you see the quadratic formula in a new light. So if you did go off and sing to your significant other or somebody, your boss or crush or whatever, the lovely song that I relayed to you at the end of our last meeting. I'm quite proud of you and thank you. And I trust that it will stick in your brain forever and ever. Amen. I'd like to remind you that if you are nervous about remembering the quadratic formula, singing it to someone to whom you can be embarrassed is the key, right? You do that once, and I genuinely promise you it will stick with you forever. This is one of those moments where you can make a decision that literally impacts your future. And it's not a difficult one. It is embarrassing, but my God, it works. I promise you this simple little technique works. So if you have any fear about that, please consider doing it. But today, what I'm going to show you is a way to think about the quadratic formula that might deepen your understanding of it just a little bit. So we're going to do that. And we're going to look at some other problems, of course. We're going to just continue talking about quadratic functions. The homework set that came due, well, we'll do that in a second. Let's do the title part. So this is MAC1105.015 section 015, which is college algebra. And the date today is the 27th, I think, 26th. No, 27th, yeah. January 27th, 2022. Today, we're going to talk about more quadratics. Specifically, we're going to explore the quadratic formula. We're going to talk about complex numbers. And something called the discriminant. Okay. So there was, as always, a homework set and a quiz that came due just now as class started. Let me quickly remind you kind of where we are in MOM. Logged back out. So quadratic functions and their graphs, homework 6 and quiz 6 came due just today. And I'll be popping open homework 7 and quiz 7 for you guys. Those will be due the following Tuesday, next Tuesday. Probably homework 8 and quiz 8 as well. So I think homework 7, quiz 7, homework 8, and quiz 8 you will be prepared to handle following today's lecture. So I will move these up so I can take a quick peek at them at the end to make sure we're not leaving you without any of the skills you need for the homework sets. But yeah, that's where we're at. That's where we're going. So homework 7 and homework 8 will be open after class today. Those will be due next Tuesday at the start of class. And this means something big. This means we're about ready for the first test. So something that I said I was going to do today that I would like to also do here is a little announcement. Exam 1 will be 1 week from today. And I believe that's the 3rd. Let's just verify this real quick. Yeah, the 3rd. 3rd of February. All right, and that exam is going to be in class. We will be taking the test here together. It is in MyOpenMath, and you will join the Zoom meeting not from your computer, but from your phone. So I'll post a Zoom link for you to join from your phone. You will join that Zoom meeting on your phone. You will set your phone up on the side of your desk somewhere I can see your hands, your paper, your lap, or your work surface, that sort of stuff. The sort of things that I'd be able to see normally walking around the room while you take a test. We will also be using some proctoring software, Honorlock, which you will access through Canvas. So on the day of the test, what you'll do, you'll come down here to this tab, which doesn't have anything in it at the moment. And you will click the link that says exam 1. You'll be asked to show your ID. So you need to have your student ID ready. As always, you need to have a webcam and a stable internet connection. Make sure that you are somewhere that your internet connection will not drop on the day of the test. We talked about having a backup. Remember, at the start of the semester, this is why. You will show them your ID, do a little room scan, and then they will take you to the test. So that is again going to be next Thursday, which is the 3rd of February. All right. There's going to be the review quiz in My Open Math to help you prepare. So yeah, any questions about the test? Okay. Interesting, but not so much a comment about the test. So I'm going to go ahead and move on. Let me just recap for you kind of what the basics of what we said about quadratics the other day. So recall. Quadratic functions are those which can be written as f of x equals ax squared plus bx plus c. The numbers a, b, and c are called coefficients. They can also be written, this is called the standard form. And these can also be written as f of x equals a times x minus h all squared plus k, which is called the vertex form. And the graphs are parabolic. They have a shape looking like this, where your vertex is this point down here, h comma k, or like this. All right. So that graph shape we said is called a parabola. That point where the graph turns around is called the vertex, and it has coordinates h comma k, where h is this number and k is this number. These all exhibit a certain kind of symmetry. And by symmetry, what I mean is you could fold the graph up over this dotted line, and it would sit right on top of itself. And that line is called the axis of symmetry. The parabola opening up corresponds to the lead coefficient being positive and the parabola opening down, is what happens if the lead coefficient is negative. So the shape on the left here, we would refer to that as opening up because the open part of the parabola here, like the top of the bowl, is pointing up. And here we would call this opening down because the open part of the bowl kind of points down, the negative y direction. We talked about how to find the vertex, right? We have a formula for h. H is negative b over 2a, and then you can calculate k by plugging h back into the expression, plugging in for x, and the number you get out will be k. We talked a little bit last time about how to find the x-intercepts. So that is where we're going to pick back up today, is talking about finding these x-intercepts. So the x-intercepts are sometimes called solutions or roots. The reason they tend to be called solutions, especially by students and tutors, is not because they're solutions to the function. Functions don't have solutions. But if you set this thing equal to 0, now you have an equation, and that equation will have solutions, and the x-intercepts are the solution to the equation f of x equals 0. The x-intercepts solutions to the equation f of x equals 0. Okay. So a lot of your homework problems center around finding the vertex, finding the max height, or setting one of these quadratic equations or functions equal to some particular number and coming up with an answer. All of that involves the sort of techniques that are necessary for calculating x-intercepts. And we said last time that you can do this by factoring. You can do this by solving using square roots if the function is in vertex form, or you can use the quadratic formula. So if you do need the homework extended, as always, just shoot me a Canvas message, and then I'll give you a late pass in MOM to go ahead and complete it. All right. So these are the sort of general pictures, right? If A is positive, the parabola opens up. Once you locate the vertex, you can draw a pretty nice graph. If you want a perfect graph, all you need is the vertex and one other point, any other point. Same thing goes if the parabola opens down. If you want to draw a perfect graph, all you need is the vertex and any other point. Oh, no, I have to wait until after I finish the lecture, unfortunately. So I'd like to look at one or two examples where we're doing some more factoring. Finding x-intercepts and solving quadratic equations. We said last time that there were kind of three main methods. You can factor, and the main tool here is the AC method. You can solve using square roots, and that's if the quadratic is in vertex form. In other words, you can only solve directly using square roots if there are no x terms. They have to only be like x squared terms. If you have like x squared minus 4x in there, if you have both of those, the x squared and the x term, then you cannot solve using square roots. You cannot like isolate the x squared term and take a square root to get your answer. You would have to factor, or use the quadratic formula. All right, so I'd like to do one more practice problem where we are factoring, and I think it would be nice to do that. Nice to do that with a homework problem where, let me see. It's all quadratic formula stuff. These are a little bit nastier, aren't they? Okay, maybe rather than grabbing a homework problem, we can do something like this. Let's do. So, for example, let's solve the equation two x squared minus x equals 3. Right? Equations like this can show up in all sorts of different ways. We need to know how to solve them. Could I solve this by taking square roots, by like isolating the x squared term and then taking the square root? Is that one of the methods I could use here?
No.
Yeah, that's correct. So Samantha's correct in saying that I could not solve this by like isolating the x squared and taking square roots. Could somebody else tell me why? Yeah, this isn't in the form where we can work with that, right? Because there is this x here. If not for that x, if I just had 2x squared equals 3, then you could divide both sides by 2 and then take the square root and you would get your solutions. But because there's this x term here, when you isolate the x squared, you'll have an x on the other side. And that means that your answer won't be like the square root of a number. It would be like the square root of a number and this variable, which is not an answer, right? So we cannot get the x alone because there's too many terms. So our choices then are to try and factor this thing or to use the quadratic formula. And my advice is to always try to factor first. So my first step here would be to subtract the 3 over. And we always need to do this. So if you're solving a quadratic equation or even any other polynomial equation, your first step should be to pull everything to one side. All right, unless you're in the special case where you can solve using square roots, your first step should be to pull everything to one side, making the other side 0. And now we want to try to factor this. And I chose this particular problem because it's going to let us illustrate the full AC method. So the AC method has you first multiply A times C. So here A is 2 and C is -3. So we get -6. Then we want to find two numbers, very similar to the example we did yesterday. Find two numbers which multiply to AC, that number you just found, and add up to the number B. And B here is -1. And this time finding those two numbers is not difficult, right? Can we think of two numbers that multiply to -6 and add up to -1?
A -3 and a +2.
Yeah, the two numbers that we actually multiplied, A and C themselves. So here, -3 and 2 work. Now that won't always be the case. It's just a coincidence here. But your general second step is to find two numbers that satisfy that relationship. They multiply to AC and they add up to B. Your third step here is to rewrite the X term using those numbers. I'm going to do that over here so you can, because it's really a part of solving the problem. So my next step here would be to rewrite -x as -3x plus 2x. I'll write it as 2x squared. That's the first term, that doesn't change. Then -x, I'm going to write as plus 2x minus 3x. And then I still have my -3 and equals 0. So we just rewrite this middle term as these guys. After that, you factor by grouping. All right. So to factor by grouping, what we do is we look at the first two terms and the second two terms separately. And we ask what factors are common here. So I'm just going to copy this down really quick so we can look at it with fresh eyes without that green underneath. Here's my first group. Here is my second group. And I'm going to pull out as much as I can from each of those groups. So in 2x squared plus 2x, there's a common factor of 2. And there's also a common factor of x. So I factor out 2x from the first group, and what's left is x plus 1. From the second group, there is a common factor of -3. So I pull out the -3, and what's left is again x plus 1. And the special thing about this method, the special thing about choosing these two numbers the way we did, is that after you do this, you're guaranteed to have a common factor between these two groups. Both of these have an x plus 1 in them. And that's not a coincidence. That will always happen. You will always have a common factor between this group and this group after you factor out the largest common factor from each of the two groups. The very last step is to take this x plus 1 factor and pull it out, thinking of each of those groups now as a single term. So I'm going to factor out x plus 1. And what's left from the first piece is 2x. What's left from the second piece is -3. So I get 2x minus 3 times x plus 1 equals 0. So wherever your quadratic equation comes from, the first thing you should try to do is factor it by pulling everything to one side. If this lead coefficient is 1, then you can use the simple factoring method that I showed you last time. If that lead coefficient is anything other than 1, then to factor it, you're going to need the full AC method here. All right, so I encourage you to take a screen cap, do something to give yourself the opportunity to remember this if you didn't write it down in your notes. If you did write it down in your notes, of course, that's great. Now that the quadratic is factored, since we have two things multiplying each other equals 0, you can set each factor to 0. If x plus 1 is 0, then x is -1. If 2x minus 3 is 0, then 2x is equal to 3. I add 3 to both sides. And that means x would be 3/2. So those are our solutions here. All right, are there any questions on this? Any thoughts or concerns? about the steps here? Any one of these steps feel at all strange? I don't mind telling you, I don't have too much pride to say this. I didn't actually learn this full AC method, right? How to factor these things when there's a number here that isn't one until like pre-calc, maybe calc 1. I was pretty uncomfortable with this. I knew how to factor if it was just x squared minus blah, blah, blah. But 2x squared or 5x squared up here, a number here would throw me for a loop. So it's okay if that's where you're at right now. But the reason we're having this conversation is to try to get you to the place where you can do this stuff, and you will be tested on this stuff. So anything we'd like to talk about here at all? Any of these steps that feel uncomfortable? You just want to know more about them, why they work, anything like that? Okay, then. So let's talk about that quadratic formula. So we know the quadratic formula. It's a formula for the roots or the x-intercepts in terms of the coefficients. X equals negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. Now there is a rule for fractions that says if you have, I'll write it down here. If you have a fraction where you've got two numbers added upstairs over a single denominator, you can split that up. We're used to thinking of it like, okay, yeah, a over c plus b over c. If I were to add two fractions that look like this with the same denominator, you just add the tops, right? And you get this. But you can go the other way too. You can take a fraction that has two pieces added upstairs and split it up into two separate fractions. It's the same thing, just backwards. What that means is I can take this quadratic formula and rewrite it as negative b over 2a plus or minus the square root of b squared minus 4ac over 2a. Most people memorize the formula like this, and that's fine. But thinking about it like this gives us some insight into what each of these pieces mean. This first piece right here, you should recognize. What is that? Yeah, if we could mute
Vertex.
that would be nice. Yeah, this is the x-coordinate of the vertex. This is h. Now this piece is a little bit weird. So let me draw a picture for you and see if we can't try to interpret that. Okay, so here is my quadratic function. This is the graph. Y equals f of x, where f of x is ax squared plus bx plus c. And we know that this point down here is the vertex h comma k, where h is negative b over 2a. The x-intercepts are these points here. And those x-intercepts are the numbers from the quadratic formula. The vertical line that I've just drawn, the axis of symmetry, is the line x equals h. Right? A vertical line is x equals a constant. Just like a horizontal line is y equals a constant, slope 0. A vertical line is x equals a constant, which means that the x coordinate right here is h. So this point right here is h comma 0. In particular, the x value there is h, which is negative b over 2a. So what this formula says is if you start at the vertex and you add this amount, you will get to one of the x-intercepts. So if you start here at the x value of the vertex and you add that square root over 2a, you get to one of the x-intercepts, because this guy right here is one of these numbers. So this piece is h. Let me call this whole thing here d. Then this x-intercept here is h plus d. And this x-intercept over here is h minus d. And what the quadratic formula is trying to tell us is that the roots or x-intercepts are symmetric about the vertex. So you start at h and you walk either to the right a distance of d or to the left a distance of d. This distance is d. This distance is d, where d is this whole fraction here. So the quadratic formula, each of these pieces has a geometric meaning. This is the x-coordinate of the vertex. This is how far you have to walk either to the left or to the right of the vertex to get to the x-intercept. The x-intercepts are symmetric because the whole graph is symmetric about this axis of symmetry, about the vertex. And the second piece, the scary looking piece of the quadratic formula, is the horizontal distance from the vertex to the x-intercept. That's what this piece is. And I think this is a really neat way to think about the quadratic formula, because it tells us it's not just some magical mystical formula with, random bullshit in it. It's the vertex plus or minus some distance. And that distance is a measure of how wide the parabola is, right? If A is really, really big, then this denominator is really, really big, which makes this whole fraction really, really small. So your parabola would be quite narrow, and the distance from the vertex here to the x-intercept would be quite small. If A is very, very small, then your parabola is going to be fat. And that means the distance from the vertex to the x-intercept is going to be large. So I wanted to show you guys this because I don't want the quadratic formula to feel like some mystical, magical thing that comes out of nowhere. I can prove the formula to you, but I don't like doing that in college algebra because it involves completing the square, and folks tend to not really be ready for that at this stage. So if you want to see the proof of the formula, I'd be happy to do it. It's not terrible, but we would do it in office hours. Okay. The piece under the square root in the quadratic formula, you have the baby. Now the kiss. The piece under the square in the quadratic formula is called the discriminant. That's b squared minus 4ac. And the discriminant tells you something about the quadratic. If b squared minus 4ac is positive, greater than 0, then you're actually going to get some numbers out of this, right? If the part under the square root is positive, then you can take its square root, you get real numbers out as a result, and you'll have two different solutions. Two distinct x-intercepts. And a fun fact, if this number is a perfect square, then you can factor that polynomial. So this is something that people ask me a lot. How do I know if I can factor a quadratic? Am I wasting my time? Some of them don't factor, right? Some of them cannot be factored by hand. Well, one way to check is to compute this discriminant. If this thing is positive, then you know you have two solutions, and that's great. But more importantly for us, if that number is a perfect square, like 4, 9, 16, 64, and so on, then you can factor the quadratic. If that number is not a perfect square, then you cannot factor the quadratic by hand, and you need to use the quadratic formula to get your solutions out. If the discriminant b squared minus 4ac is equal to 0, that means that there is one x-intercept. And if b squared minus 4ac is negative, less than 0, well, that means that the quadratic formula is going to tell you to take the square root of a negative number. And you know that you don't get real numbers out when you do that, right? We cannot take the square root of a negative number. Or we can, but the result is not a real number. As far as the graph is concerned, this means there are no x-intercepts. In other words, the solutions to the equation f of x equals 0 are not real numbers. And a very reasonable question is to say, well, if they're not real numbers, what the fuck are they? They're called non-real complex numbers. Okay, and that's what we're going to talk about next. We're going to talk about non-real complex numbers. So a little bit of background. Maybe I'll hold here for a second. This is definitely something that you will be tested on, so make sure you know this. Screenshot, clearing the notes, whatever you need. The quadratic formula was discovered just prior to the Renaissance in Europe. And at that time, mathematicians argued quite a bit about whether it was possible to take square roots of negative numbers. Well, remember that the square root is supposed to be a number such that when you multiply it by itself, you get the original number back. Right? So like the square root of 4 is 2, because 2 squared is 4. But the square root of, say, -1 would be what? Because if the square root of -1 is positive, a positive number squared is definitely positive. And if the square root of -1 is negative, well, a negative number squared is also positive. So the square root of -1 doesn't exist. Because if it were a positive number, then squaring that would give you another positive number, so not -1. And if this were negative, squaring a negative number also gives you a positive number, so it couldn't be -1. And this was the general thinking for a very long time. Eventually, someone said, I'm going to do it. I declare the square root of -1 to be the number I. This is not a real number. But okay, let's call it imaginary. Let's just imagine that there is some number such that when I square it, I get -1. Turns out this person was a friggin' genius. This is such a good idea, even though it's counterintuitive to everything we understood about mathematics up to that point. There could never be a real number such that when I square it, I get -1. There could never be a real square root of -1 because when you square any real number, the result is always positive. But if you allow me to pretend like there is such a number, then I can do all sorts of shit that I couldn't do before. So I squared, this allows us to compute, this allows computation of roots of all negative numbers. All numbers, positive and negative. If you've ever wondered what my background picture is here, I mentioned this once before, this is actually the complex plane. This number, so right at the top here, this little black diamond-shaped hole in the middle of the orange ring, that's the number I. Over here, this big black hole here, that's the number 1. Over here is the number -1. So this horizontal line is the real line. 0 is right here in the middle. This is 1. This is -1. 2 is over here to the right. We think about the imaginary numbers as being perpendicular to the real numbers. So up here is I. Down here is -I. And the system overall we call the complex numbers. Before I say anything more about complex numbers in general, I just want to get some practice taking square roots. If I want to take the square root of -16, I can do that by using some algebra rules for square roots and this fact that the square root of -1 is the number I. The first step is to realize that -16 is -1 times +16. And then to remember that square roots play nice with multiplication, meaning if you have two things under a square root multiplied, then you can take the square root of each of those things separately and multiply them. Now the square root of -1, we declared to be I. Consequences be damned. So that first part there, that's I, the imaginary unit. And the square root of 16, well, that's a number that we know how to handle. The 16 is 4 squared, so this is 4. Or usually we write the I at the end, 4I. Let's try another one. How about the square root of -27? Well, that first step is the same. 27, -27 is -1 times +27. So I can split that up as the square root of -1 times the square root of +27. Square root of -1 is I, sure. But what do I do with the 27? Does anybody remember how to handle square roots like these, where the number inside is not a perfect square? Can I simplify this at all?
You can pull out the 9 and then leave a 3 inside, so it'd be 3I.
Yeah, so I've got an
Right.
I from this piece, and I'll write it out really, really carefully here. So 27 is 9 times 3. If I can split that up further, this is I times the square root of 9 times the square root of 3. Now the square root of 3 is an irrational number. 3 is not a perfect square, so there's nothing I can do there, but 9 is a perfect square. So this is I times 3, the square root of 9, times the square root of 3. Or you could write it as 3 root 3 times I. I'm just putting the I at the end. And as you simplify the answers you get from your quadratic formula, you will need these sort of skills, right? Not just the I stuff, but also the skills to clean up square roots in general. Let's take a look at a homework problem. Let's grab something from this first guy. All of this is factoring. Yeah, we did some factoring already. So let's find the roots or zeros. So let's take this guy, number 8 from the first new homework, 15x squared equals 11x minus 2. Again, my first step should be to pull everything to one side. This is not in that vertex form. I have both x's and x squared, so I can't solve the square roots. We're going to need to either factor this or use the quadratic formula. So I subtract the 2 over so that the whole thing is equal to 0. That's the important first step. You have to have the right-hand side being 0. I can compute the discriminant. To see if this factors. And if this thing turns out to not factor, well, it's good that I computed the discriminant because that's a part of the quadratic formula anyway. I would need that anyway. So b squared, that's negative 11 squared minus 4 times a is 15 times c is negative 2. 11 squared is 121 minus 15 times 2 is 30. 30 times 4 is 120. And this is negative, and this is negative. So this will be plus. What did we say? 30 times 4 is 120. So when you add these two together, you get 241. Now, if you're not sure if 241 is a perfect square, nothing wrong with using your calculator. This takes forever to boot up. So if we want to check whether 241 is a perfect square, I can take 241 and put it under a square root. Oh, let me do it. To get your square root, you can type second and then this x squared button, and then 2, 4, 1. And I get 15.5241, blah, 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 blah. Not a perfect square. So this quadratic doesn't factor. Can't be factored by hand. But these calculations are not wasted. We need to use the quadratic formula. And again, if you write it down before you plug in, you will make fewer mistakes and remember the thing more easily. One of these pieces, the b squared minus 4ac, the hard piece, I already calculated that. That's 241. B is negative 11, so this is negative 11 is positive 11, plus or minus the square root of b squared minus 4ac is 241. We already calculated that, so we don't need to recalculate it. And we're dividing this by 2a. Well, a is 15, so 2a is 30. While I cannot factor the thing by hand, there will be x-intercepts because this discriminant, while it's not a perfect square, it is positive. So because this is a positive number, I do expect to find two solutions to this equation. They're just not going to be very nice numbers. And if we want to figure out what those are, I'll call them x1 and x2. The solutions are I'll show you how to enter this in the calculator. You do need to be careful. I'll take the plus first. 11 plus the square root. Again, hitting second and x squared to get my square root, 241. If I were to say now divide by 30, would that be correct?
No, you gotta hit equal.
Good, yeah. So I want to divide this whole thing by 30. And if I were to just type divide by 30 right here like this, that's not going to divide the whole thing by 30. That's just going to divide the square root of 241 by 30. So we don't want to do that. Go ahead and hit enter. Get that whole numerator and then divide by 30. The other option is to use parentheses. So this first number is 0.884139, blah, blah, blah. 0.8841, I'll say 39. Always give yourself more precision than you think you need. Wait to round until the end. All right. The other number comes from the minus in the plus minus. So I'll take 11 minus second square to get my square root, 241. Hit enter, then divide by 30. And I get negative 0.150806. 0.150805. All right, and then we could round these wherever we want to. Those are the two solutions to this quadratic equation. They're irrational numbers, so these decimals are approximations. The exact values come from the quadratic formula, like this thing. Any questions about how we got these solutions? Okay. Let's try something where we don't have real numbers. How would you solve this?
Square root.
So here I just have an x squared term. I don't have any x terms, just x squared and constant. So here we can use the square root, because there are no x terms, i.e. this is in vertex form. So if x squared plus 4 is equal to 0, that's the same as saying x squared equals negative 4. And that might look like a real problem at a first glance, because this is a negative number and my next step is taking square roots. But if you are comfortable with complex numbers, with imaginary numbers, then you can go ahead and take the square root the same as you normally would. You get x equals plus and minus the square root of negative 4. And then that square root of negative 4, we're going to simplify the same way. That's 4 times negative 1 plus and minus, which is plus and minus the square root of 4 times the square root of negative 1. Square root of 4 is 2, so that's plus minus 2, and the square root of negative 1 is I. So our solutions are x equals 2i and x equals negative 2i. Okay, let's try something a little tougher. How about this guy? I can't solve this using square roots because it's not in that vertex form. I have both x squareds and x's. So I think maybe I can factor this, or if not, then I'll use the quadratic formula. We can compute the discriminant. b squared minus 4ac. B here is 1, so this is 1 squared minus 4 times 1 times 5, which is 1 minus 20, or negative 19. So that's not positive, right? This is negative. So there are no real solutions. Definitely doesn't factor. Right? The only case where you can factor by hand is if your discriminant is a perfect square, a positive number that is a perfect square. So we'll use the quadratic formula. Tells me that my solutions are negative b plus and minus the square root of b squared minus 4ac over 2a. Negative b is negative 1 plus and minus the square root of b squared minus 4ac is the thing I cooked up a minute ago. So it's the square root of negative 19 all over 2a. Well, a is 1, so this is 2. And these aren't pretty numbers, but we can clean them up just a little bit. 19 is prime. So I can't pull out any perfect square factors there, but I can take that negative and say, okay, the square root of negative 19 is the square root of 19 times I. And downstairs I have the 2. And my question is, like we did here, where we wrote those two solutions individually, can I do that here? I don't want to use the calculator. I'm not looking for an approximation. Besides, I've got these I's in there. I don't want to deal with that shit.
Yes.
Yeah, how can I do that?
One of them is just going to be negative 1 plus square root 19i, and then the other one will be the negative.
Good. So I'll have negative 1 plus the square root of 19i over 2. And the other guy is negative 1 minus the square root of 19i over 2. And that's it. Those are your solutions. Now you can write these in what's called the standard form for a complex number a little bit more nicely by using that trick I showed you for splitting up fractions. Right? Remember, fractions, you can split them up across the top. So this is negative 1 over 2 plus the square root of 19 times I over 2. And the second guy could be written as negative 1 over 2 minus the square root of 19 times I over 2. All right. Yes, we do have an in-class activity plan for today, but I did not post it this morning. Let me take a look here. We may have to push that back just a little bit. So I have your activity, but because I haven't distributed it, I think it's probably better if we do this next Tuesday as preparation for the test. Probably that's what we'll do. So we learned today about the discriminant, and we've talked about graphing quadratics. Here is the activity. Maybe, what time do we have left here? Not a whole lot, right? Yeah, it's 10:37. I don't think we have quite enough time to fill in our activity. So what I'll do is I will go ahead and post this for Tuesday of next week. We'll go ahead and do the activity then. It's pretty straightforward, but I want to make sure we have time since there's only like 8 minutes of class left. We'll do the activity next time. There is one other thing that I want to show you guys before I let you go for the day. Take a quick look at your homework, make sure I'm not leaving anything out that you need. We haven't looked at many of these application problems. Maybe we should do something like this. All pretty straightforward. Yeah, let's do something, before I let you go, let's do something like number 23 here, where we have a real world thing. I know these word problems tend to be a bit of a headache. Yeah, let's do something like this. Yeah. So before I transition to that last problem, I want to talk about the complex numbers as a set. This will be very quick, I promise. So if I is the square root of -1, then we can form what are called complex numbers a plus b times I, where a and b are real numbers. These add, subtract, multiply, and divide exactly how you would think they do. You can add two complex numbers by adding the real parts and the imaginary parts. So a here is called the real part. B here is called the imaginary part. Perform the indicated operation. Dividing complex numbers is a little bit tricky, and I'm not going to make you guys do that here. So I'm just going to give us a couple little things to do. 2 plus 3i plus 6 minus 10i. Minus I minus 2 plus I. All right. So here's two little bits of arithmetic we can do with complex numbers. If I want to add two complex numbers, think of I as a variable. You can treat I the same way you treat a variable. So you take the real parts and add them up. 2 plus 6 plus, and then you take the imaginary parts and you add them up. So 3i minus 10i. And you get out what you think. 2 plus 6 is 8. 3i minus 10i is minus 7i. And if we want to multiply these, you would FOIL the same way you would normally FOIL. So your firsts are 1 times 2, which is 2. Your outers are 1 times I, which is I. Your inners are minus I times 2, which is minus 2i. And your lasts are minus I times positive I, that's negative I squared. And the reason I wanted to show you this is specifically about how to handle the I squared. So whatever this is, it's 2 plus I minus 2i is minus I, and then minus I squared. What is I squared?
Is it -1?
Yeah, very good. In fact, a lot of mathematicians take this to be the definition of the number I, rather than calling it the square root of -1. But this is because I is the square root of -1, right? Either way of thinking about it is fine. So over here, this is 2 minus I minus -1, because the I squared is -1. And subtracting -1 is the same as adding 1. So this is 3 minus I, that's what we get. Okay, adding, subtracting, multiplying complex numbers, all very easy. All works exactly how you would think it does. The only catch is when you multiply complex numbers, you're going to run into I squared from time to time. And I squared, you have to remember, is -1. One last little fact here. All real numbers are also complex. They just have imaginary part equal to 0. So for example, the real number 5, I can think of as 5 plus 0i. I know it's silly. The real number -pi, I can think of as -pi plus 0 times I, and so on. Again, these make for silly kind of trick questions that show up from time to time on the 1105 department final. So in our last seconds here, what I want to do is look at that application problem. Let's go ahead and do that. We're told that the horsepower of an engine, the power output of an engine, is a function of its RPM, right? How fast the engine is spinning. The specific function given here, engine and jet, whatever we'll use this, yeah, -x squared over about 30,000 plus 5x over 28 minus 19. And we want to find when does the engine reach max power? And what is that max power? And there are many variations on this, but what you're trying to do, x here is the RPM of the engine, the speed of the engine, and the output, y, is the power. So if you want to find when the power is as large as possible, what you're looking for is the max on that graph. We know that the max will be at the vertex, right? This is a quadratic. It's a graph is a parabola. It opens down, something like this, right? So the vertex here is going to be the max. This happens when x is equal to h, which is -b over 2a. So we need to figure out what a, b, and c are. Let's say that up here. What is a? Careful. So a, remember, is the number multiplying the x squared, but I've got this 30,000 down here. So a is really -1 over 30,000. Right? It's everything that's attached to the x squared. So this -x squared over 30,000 is the same as -1 over 30,000 times x squared. The same sort of logic will tell us b. Can somebody else help me with b?
5 over 28.
Very good. Yeah, positive 5/28. And C is not hard to see, right? C is negative 19. Okay, so sorting out A, B, and C from this kind of weird form is not super obvious. And now we have some weird fraction arithmetic to do down here. Let's look at it. If I just plug things in, then I get negative B is 5/28 divided by 2 times A is negative 1/30,000. And this is a pretty messy looking number. Got a negative out front, got a fraction upstairs, I've got a non-fraction and a fraction downstairs. Here's how you clean this up. First, write the top and bottom as single fractions. So the negative is still up front. I'm going to have a big fraction, and the top and bottom are both fractions. The top is just 5/28. The bottom, 2 times 1/30,000, or negative 1/30,000, is negative 2/30,000. And you can simplify the fraction down here if you want to at this step, but you don't have to. We can simplify later. Now that I have a big fraction with one fraction upstairs and one fraction downstairs, I can come over here, leave the top alone, and flip and multiply by the bottom. But it's very important that you simplify the top and bottom into individual fractions first so you know what to flip. Now, overall here, I had a negative out front and the bottom is negative. So the negatives are going to go away. The whole thing is positive. Finally, we just have to simplify. And some of this can be done by hand. 30,000 divided by 2 is 15,000. So this is 5/28 times 15,000. And then we can put this into our calculator if we want. I'll do it in Wabbit. So I have turn on 5 divided by 28. I'm going to take that number and multiply by 15,000. And I get 2,678.571429.
Isn't it 150,000?
I think it should be 15. 30,000 divided by 2. Was this is 30,000
I
here,
got
right?
you.
Yeah. So the max power is reached when the RPM, the speed of the engine, is about 2,678. I don't know where they want us to round. We'll say 0.57. How do I find the max power itself? So this is the answer to part A. Part B, what is the max power? How would I find that? Well, what we just found is h, right? The x-coordinate of the vertex, which tells us the RPM, which makes this thing as big as possible. This thing is the power. So if I want to know what is the max power, remember, like, where is the max versus what is the max? It's not that we're going to plug 0 in for x, we're going to plug something else in for x. So we found that the max occurs when X is 2,678, if I want to know what is that max, I'm looking for the Y value of the vertex. So the max power is K, the Y value of the vertex. And the way you find K is by plugging in H. Which is this number. So that max power is going to be negative 2,678.57 squared divided by 30,000 plus 5 times 2,678.57 divided by 28 minus 19. And again, this is definitely a job for the calculator. You wouldn't want to do this by hand. You do need to be very careful on how you enter things. So negative, parentheses, just as I've written it there, 2,678.57, close parentheses, squared, all divided by 30,000. And what I'm going to do is crunch these terms one at a time. So this first piece is negative 239.16, just rounding to 2 decimal places here, plus. Now the next piece is 5 times 2,2,678.57 divided by 28. And I get 478.32, rounding to that same second decimal place. And then minus 19 is minus 19. So finally, I can take these numbers and add them up. Negative 239.16 plus 478.32 minus 19. And I get 220.16. 1.16, that's neat. All right. So this would be your max power, and the units they're using here, power per approximate with this horsepower, right? So this is horsepower. So that language we discussed when we first introduced mins and maxes is the thing that saves the day here. Where is the max? Is the input. For what input do you get this max? What is the max? Is the output. So if I'm asking, when does this happen? When is the power maximized? When do you generate the most money? When is the cannonball at its highest height? Any of those things, you're looking for the X value of the vertex. When or where does this happen? X value. What is the max power? What is the max height of the cannonball? What is the max money generated? That's always the Y value of the vertex. And you always get the Y value of the vertex by plugging in the X value to the original equation. So you usually got to find that H first for any of these problems, regardless what they're asking for. Okay, this is where I'll wrap it up for today. We're going to do that activity on Tuesday of next week. Your exam is going to be Thursday of next week. I will also be assigning you a little take-home activity. We'll call it a project. It's just a short worksheet. You won't have a hard time with it. That, together with the material in My Open Math, is meant to prepare you for the test. If you have any questions, I have an office hour. It's going to start in 3 minutes. Otherwise, just try to stay on top of the homework. Make sure you come to class on Tuesday because we're going to do the activity then, and I will send out that project through Canvas. So watch your Canvas announcements as well. That's it from me, guys. Take care, and I'll see you in office hours or next time.